Okay. Side at which you can get the context and the list of actual statements that I'm addressing here. And if you're in my class, you know where to look for the 1905-02 document. But in case you lose track of that, you can always look here. Okay. Now, graph a polynomial or rational function. I'm going to need to get this out of the way because I don't want it to get hurt. Okay. So here's a rational function. It's just a polynomial divided by a polynomial. Now, the polynomial isn't always factored, and this might not all be completely factored, because of course this could be factored. Okay? If you have a polynomial that can't be factored, you factor it. Numerator polynomial, you factor the denominator polynomial. Now, in general, real world situations, lots of luck factoring. Okay? Generally can't do it, but still, this is the principle that we use to graph a polynomial or rational function. Okay. First, you find the zeros of the numerator, which are x equals 3, because, again, using the zero property of multiplication, in order for the numerator to be 0, this or this or this has to be 0. So if any one of these is 0, the whole thing's 0. So x equals 3 makes this 0, so it makes the numerator 0. Okay? X squared plus x, 2, you got a negative discriminant. No real zeros, and that's been addressed elsewhere. And x squared plus 5x plus 6 equals 0. You could use a quadratic formula, but it's just x plus 3 times x plus 2 equals 0. X equals negative 3, or x equals negative 2. Very straightforward. So the numerator has zeros at 3, negative 3, and negative 2. Now I can come down here, draw myself an x-axis, and indicate those zeros at negative 3, at 3, and at negative 2. Put a little x there to indicate that these are zeros. Zeros in the denominator. Well, x squared plus 2 no real solution, so there's no zeros there. X minus 1 squared equals 0, x equals 1. Now, any zero of the denominator gives you a vertical asymptote unless it happens to match a zero of the numerator. And I'm not going to talk about that right now. Okay, so here at 1, you're going to have a vertical asymptote. That 1 now looks like part of the dotted line. Okay, so what do we do with this? Well, this function is continuous, or continuous accepted asymptotes. It can change sign only by passing through the x-axis at a 0 of the numerator, because of course the zeros of the numerator are the only x values that make the entire fraction 0, or by crossing a vertical asymptote since the function is not continuous at a vertical asymptote, that is, it doesn't have any value at the vertical asymptote, so what happens to the left and what happens to the right of a vertical asymptote could be anything. Okay, if it's got to approach infinity or negative infinity at both sides, go to infinity on the left and negative infinity on the right, go to infinity on both sides, go to negative infinity on both sides, go to negative infinity on the left and infinity on the right. Okay, so, in other words, it acts like a reciprocal power function, right? A power function with a power with a negative power. Okay, like the 1 over x or the 1 over x squared, or vertical stretch of either of those. Okay, so what we know is the function is either always negative or always positive all the way from negative 3, well, all the way to the left of negative 3. It's 0 at negative 3. Okay? So we have to determine whether it's always positive or always negative. The easiest way to do that for an infinite interval is just assume, okay, we've got a huge negative number, way left, huge negative number, and we plug it in here. What do we get? Well, the square of a huge negative number is going to be negative, positive, and so is this square. And the square of a huge negative number is going to be way bigger than any fixed multiple of that negative number. Just let the negative number get huger than the coefficient, and way bigger than any constant number. And same thing here. So all three of these will be positive if x is a huge negative number. Now, x minus 3 will be negative, won't it? Because if x is a big negative number, well, any negative number, this is going to be negative. And x minus 1 is going to be negative as well for a big negative number, but you're squaring it, so it's going to be positive. This means that this, and this are positive, this is negative. If you multiply a negative by a bunch of positives and divide by some positives, it's still going to be negative. So we know that the function is negative on this interval. Okay? Now, in class, I ask people to write down like negative, positive, 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 positive. So you write down negative, positive, 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 and it's a good idea, if you're taking my exam, to do that so I see what you're thinking. It's quicker than trying to explain it in writing. And if you are doing this, even if you get it wrong, you get more partial credit than if you just write down the wrong thing here and don't justify it. Okay. In any case, this is what you get. Now, you go over here, and you're going to find that x minus 3 is still negative. And all the rest of these, no, never mind. X minus 3 is still negative. X squared plus 5x plus 6 is now negative. And all the rest of these are going to be positive. Okay? You're going to get 9 plus 6 minus 15 when x is negative 3, but if you go a little less than negative 3, and that added up to 0, you're going to get a positive. So you could write it out, negative, negative, going in order here, and then here, positive, positive. Because again, both terms of the denominator are always positive, and that's 2 negatives with 3 positives. You multiply them out, you get a positive. Doing the same thing in this interval. Now this interval conveniently contains 0, and since the sign is the same everywhere on this interval, you can just plug in x equals 0, and you find you have negative 3, positive 2, positive 6, positive 2, and positive 1. Okay? So again, you would get a negative and a bunch of positives, which would give you a negative. So the function is negative on the interval from negative 2 to 1. Now that's at 0. But since it's so at 0, and since the sign can't change between here and here, it's so everywhere on the interval. Okay? Now between 1 and 3, we check it out. And we're going to find it's still negative. Now another technique for doing this, I didn't want to do it between -3 and -2. I'd had to use a fraction, but I could have. But between 1 and 3, you could let x equal any integer between 1 and 3, like 2, and pretty easily plug it in and evaluate every term. In any case, you would find out that you still have a negative and 4 positives. Get a lot of positives because the denominator terms are always positive. Okay, now you go to the right of 3 and all of a sudden what changes? X minus 3 is no longer negative. Now you could think if x is a huge positive number, what are you going to have? Well, a huge positive number minus 3 is still a huge positive number. So you're going to have positive, and all the rest of these are easily seen to be positive. So the graph is positive here. Okay? Now there's a little more to it, but the numerator, if you multiply all this out, you're going to have an x to the 5th. The denominator is going to have an x to the 4th. Okay, if you multiplied it out and did a long division, it'd be a little uglier. But when you divide the x to the 4th into the x to the 5th, you're going to get an x. And then everything else you get is going to be a remainder. Meaning that this graph acts a lot like the graph of y equals x if you go far to the right or far to the left. Okay? And without going into that detail, that's something you want to consider. I'm not going to address it for brevity right here. But I'm going to say that, okay, when x is a big negative number, you got a 5th power of a big negative number here, a 4th power of a big negative number here. You're going to end up with a big negative number. And if you go to the right with a big positive number, naturally I wrote where I need to write a symbol, but the graph is going to go like this as you move to the right. So it's going to come up from negative values. It's got to go through the graph to the x-axis at the zeros. Okay, it's got to go through the x-axis at a 0 here. And then it's got to approach this asymptote, which means it gets closer and closer to the vertical line, but it keeps going down and never gets to the vertical line. And it does that through negative numbers, so that the graph is negative up to 3, negative 3, positive between 3 and 2, negative between negative 2 and the asymptote. Now on the other side of the asymptote, what happens? It's still negative. That means it's got to come up toward this 0 from big negative numbers. Then it comes through here, and then it just kind of goes off in this direction. So that's what your graph is going to end up looking like. Now that's a pretty good summary of the main techniques you use in graphing a rational function.